So the fact that we're doing simple stoichiometry, if you look, I think at part 7, it's not simple stoichiometry. So it's limited supply stoichiometry. So we'll introduce this first. This is what you'll be doing in lab tomorrow. So you guys did some work balancing equations, and that big number to the left of the species is the stoichiometric coefficient, right? The stoichiometric coefficient. You balanced it so you had the same numbers of atoms of each type of element on both sides of the reaction arrow. That stoichiometric coefficient tells you relative amounts. It's like, I do liken it to a recipe. It tells you how much of the reactants in terms of moles and how much the products you're going to form based upon that amount of reactants. That's the stoichiometric coefficient. So in general, stoichiometry is just relative amounts. And it's usually in moles, it's not in grams, because a mole, remember, goes back to a counted particle, and grams is just grams, okay? So it's relative amounts, usually in moles. So this is a balanced equation. 2 Mg reacts with 1 O2 to form 2 MgO. We could do the brick wall, and we have the same number of atoms of magnesium oxygen on both sides of the reaction arrow. Now, if I was balancing it, I would consider it as like magnesium, I'd go like atoms and molecules, or actually formula units. I would say that 2 magnesium atoms reacts with 1 molecule of O2 to form 2 formula units of MgO. That's just kind of how I think, right? But do you remember when we were talking about balancing equations, you can multiply through by like 2 and get another set of stoichiometric coefficients? Well, along those lines, what if we say, instead of just individual atoms and formula units, what if we said that those relative numbers of 2, 1, and 2, those were all relative moles, okay? So now it goes like this. We have 2 moles of magnesium, I love that phrase, react with 1 mole of O2 molecules to form 2 moles of MgO formula units. So we just, because remember mole, I mean, don't let it get lost in the shuffle. 1 mole is 6.022 times 10 to the 23rd of those things. Okay, something you can sink your teeth into. So that idea of using those stoichiometric coefficients as relative moles in your balanced equation is kind of what's behind stoichiometric calculations. So stoichiometric coefficients, right? It's the recipe. It's the relative number of particles, or taking it up a notch, moles. So in doing stoichiometric calculations, I think I mentioned a minute ago, it looks kind of like this. You know, if we have 2 reactants going to form 2 products, right? So a stoichiometric calculation, and it's usually grams, is basically, I know grams of this, and I'm trying to get to grams of this. Or, I know grams of this, and I'm trying to get to grams of this. Or, I know grams of this, and I'm trying to get to grams of this. You got the idea? So those are 3 different problems. What they have in common is, I know grams of something, I'm trying to get to grams of something else. That's a stoichiometric calculation. Okay. So in order to do these, what are these? What? Like a gram to gram problem, okay? In order to do these grams to grams problems, which we're ultimately going to do, we need to have the balanced equation. I'll show you how we use the balanced equation to our benefit. So to our benefit, from the balanced equation, we are going to come up with these ratios. When I go like this, there's a number here, and there's a number here. And actually, this is going to be moles of something, divisor line, moles of something else. That's my stoichiometric ratio. I'll use the term stoichiometric ratio. OpenStax uses stoichiometric factor. So we're going to pick those relative moles off of our stoichiometric coefficients from the balanced equation. So it looks like this. Going back to our magnesium reacting with oxygen like this, we could come up with a series of different kind of relative moles. And which stoichiometric ratio you're going to go with depends upon what you have and what you're trying to get to. It's all about factor labeled, so we're going to make sure our units cancel and all that. So for instance, if I want to focus on the two reactants, magnesium and oxygen, or molecular oxygen, O2, I could come up with these statements. These are two stoichiometric ratios. I'm not using them right now. I'm not using them right there, but I could use them. The way this reaction goes down, 2 moles of magnesium will react with 1 mole of O2. Now it's about making units cancel. So if I want units of moles of magnesium to cancel, I'm going to go this the other one. I'm going to say 1 mole of O2 will react with 2 moles of magnesium. Now that's focusing on 2 reactants. But I could focus, and I've got 2 more, okay? So I could focus on one of the reactant and the product. Now this is where sometimes students are like, well, the stoichiometric coefficients are both 2. So I know that we could reduce this. But I like to leave it just like this, because I like it because it emphasizes that this 2 came from here, and this 2 came from here. So all these ratios are doing, and again, we're not using them, just showing the possible ratios with these 3 things. 2 reactants and 1 product. Of course, the relationship the left and the right one have are the inverse of each other. So the inverse could also be said. One last one. Looks like what's the relationship with regard to moles of O2 and moles of MgO? We can do 1 mole of O2 over 2 moles of MgO, or 2 moles of MgO over 1 mole of O2. So these are 6. So while we're on this slide, we're going to call this A, B, C, D, E, and F, because we're going to work a problem using this balanced equation. And one of these 6 are going to be the one that we're going to use to get us down the road. We're going to work a few problems. All right. So when I work a stoichiometric calculation where I'm going from grams of something to grams of something else, it's kind of like you saw me do this on the board. This probably looks foreign to you, I don't know. But this is my balanced equation, and then underneath my balanced equation, I write what I have, or under the species of what I have, I write that amount and what I'm trying to get to. It's just a habit I've gotten into, and I think it helps. So in this case, it says how many moles of O2, so question mark moles of O2 is needed to react with 0.245 moles of Mg. So under Mg, I put 0.245 moles. Now this is what I would call, this is like a baby stoichiometric calculation. It's kind of the heart of the stoichiometric calculations when we get going. The one I showed you over here that's different than this is we're going from grams to grams here. And this is I'm just going from moles to moles. So this one's a little easier. So that's the first problem. And the second problem looks like this. So how many moles of MgO? So I'm going to put another row here. I'll put question mark moles under my MgO is produced. Now this is not worded very well, but it's assuming that we have 0.245 moles of magnesium. So I'm going to put 0.245 moles of magnesium over there. The stoichiometric calculation is always going from, you're given information about something, you're asked to find information about something else. It's a mixed bag. It could be reactant to reactant, it could be reactant to product, it could be product to product, it could be product to reactant. All right. So in order to work this, oh, I should have asked you guys, drum roll, which one is this, A through E? Which one is this one? B. B? Okay, thank you. It's B a few slides ago. So if we want moles of magnesium to cancel, because that's going to be our first term, 0.245 moles of magnesium, looks like this. over 1. Oops, sorry. This is my emphasis. Yeah, this is my emphasis. So this is problem 1, problem 2. So much for asking me what we should go with. So the first problem, we're going from moles of magnesium to moles of O2. So if we want moles of magnesium to cancel, that is going to go in the bottom. Since there's a stoichiometric coefficient of 2 in front of magnesium, the 2 comes with it. To moles of O2, stoichiometric coefficient of 1, that goes in the top. We'll go from moles of magnesium to moles of magnesium oxide. They both have a coefficient of 2. So make sure you kind of know these are stoichiometric ratios from the stoichiometric coefficients in the balanced equation. All right, here we go. If we put 0.245 moles of magnesium over 1. Now does this, I bet you, well, this will become more obvious. I know it's obvious now. You can't just put moles because we got 2 things of moles. We got moles of magnesium and moles of O2 here. And then if we go with the ratio we said of B, we put 1 mole of O2 over 2 moles of magnesium. And again, this 1 came from this 1 here. This 2 came from this 2 there. Now these ratios will be exact. There's no uncertainty there. So 3 sig figs. I got 0.123 moles of O2. And then the follow-up question, the first term is going to be the same, 0.245 moles of magnesium. And then what is the ratio going to be that goes next? 2
magnesium oxide.
Yep. 2 moles of magnesium oxide over 2 moles of magnesium, exactly. So I can do the math there. Get 0.245 moles of magnesium oxide. And it kind of makes sense, like the amount of O2 that's going to react moles-wise, not grams, but moles-wise, the moles of O2 that's going to react is going to be half of the moles of magnesium. You can kind of see that. The moles of magnesium oxide formed are going to be the same as the moles of magnesium. And I just feel I just got recipe written all over it. It's just like a recipe. Okay. Well, that was the heart of a stoichiometric calculation. Now we're going to take it up a notch. And instead of that, this is probably what you're going to run into. So it says what mass of oxygen, so I'll find O2 and I'll put question mark grams. What mass of oxygen is needed to react with 0.30 grams of magnesium? And I'll kind of diagram it here, but it's on the next slide too. I'm going to start with magnesium instead of the O2 because that's what I know something about. I am going to go from grams of magnesium to moles of magnesium using the molar mass. And then once I have moles of magnesium, I'm going to skip over and go to moles of O2 using the stoichiometric ratio. And then to finish up, I'm going to go from moles of O2 to grams of O2 using its molar mass. So that's kind of what we have going on here. Well, let's see. So notice what we can't do. This is a drama here, okay? We can't use the fact that 2 moles of magnesium react with 1 mole of oxygen. We can't use that stoichiometric ratio with grams. That's a big hairy deal. It will not work. But we're going to kind of go around. So here we go. Grams of magnesium to moles of magnesium using its mm, or molar mass of magnesium. I love that phrase. And then the moles of magnesium to moles of O2, kind of like we did before, using a stoichiometric ratio from the balanced equation. And then to finish up, we gotta kind of unpack moles back to grams again. And so we're gonna use, for O2, we're gonna use the molar mass of O2. So this is a very common, I use the word cadence. It's got a very common rhythm to it. Start with mass of something, convert it to moles, using its molar mass. Then you go to moles of what you know to moles of what you don't know using the stoichiometric ratio, the stoichiometric coefficients from the balanced equation. And then you go from moles of what you didn't know to grams of what you didn't know using its molar mass. So here we go. And sometimes students will want to like break it up into 1, 2, 3 parts. But what you're going to see me is I've gotten in the habit, and maybe you will too, of just stringing it all up. So here we go. Okay. So we're going to need the molar masses. And actually, I went ahead and knocked out the molar mass of everything, even though for this problem, we don't need the molar mass of magnesium oxide yet, but we will here in a minute. So for magnesium, from the periodic table, you're looking at 24.31 grams per mole. For O2, you take 2 times 16.00, so you're looking at 32.00 grams per mole for molecular oxygen. And then for magnesium oxide, you take 24.31 plus 16.00, and you get 40.31 grams per mole. So a lot of times when I'm doing stoichiometric calculations, I'll do just like this. I'll say I'll usually say mm of mg, mm of O2, mm of MgO. So working on ahead. All right. So the first term is going to be that 0.30 grams of magnesium over 1. So what does the next term look like? Very good. 1 mole of magnesium over 24.31 grams of Mg. Perfect. I'm liking it. So what does the next term look like? Very good. 1 mole of O2 over 2 moles of Mg. Perfect. And then what does the last term look like? It's the molar mass of O2. Yeah. So, 32. Yep, very good. 32. 32.00 grams of O2 over 1 mole of O2. Perfect. The molar mass of O2. Now get your fingers ready. So we've talked about rounding. There's exact, 1 to 2 are exact. Of course, the 1s and the molar masses are exact. But there's uncertainty here, here, and here. So how many sig figs? 2. I'm liking it. So got a nice round number of 0.20 grams. And then units would be, of course, grams of O2. So I haven't looked at it recently because it's been a while since I've done the answer key for all y'all's homework. But I think you'll get, I laugh because I think you'll get some homework, get the old memory. It's called muscle memory. When you guys do this, it like creates it's a good thing at doing these. All right, let's do another one. Let's do a related problem. So in this case, it said what mass of magnesium oxide, so question mark grams over here under my magnesium oxide, is produced when we have 0.30 grams of magnesium. Notice this says, and we'll talk about this more on Friday, when it says you have sufficient oxygen. So that means you have enough. And actually, the problem we just did, actually, your enough would be what? 0.20 grams? You have at least 0.20 grams. Now, you might be like, Mrs. Snipes, I'm betting if I add this weight, and if I add this weight, if I add the weight of my magnesium, if I add the weight of my O2, I bet that's going to be the weight of my MgO made. And right. You're like thinking that way. But let's go ahead and knock it out. So in this case, we're going to go from, We're going to go from grams of magnesium to moles of magnesium. They're going to go from moles of magnesium to moles of magnesium oxide. They're going to go from moles of magnesium to oxide to grams of magnesium oxide. It's like a little bucket. Not a circle, is it? Okay, so here we go. The first term is going to be that 0.30 grams of magnesium over 1. So what's the next term?
1 mole of Mg over 24.31 grams.
Yep. 1 mole of Mg over 24.31 grams of Mg. Perfect. That's the molar mass. Then what? We're on our way to magnesium oxide.
2 moles of magnesium oxide and 2 moles of magnesium.
Yep. 2 moles of magnesium oxide. This 2 came from here, over 2 moles of magnesium. Perfect. And so what's the last one?
The molar mass.
The molar mass of magnesium oxide, exactly. So we'll go with 40.31 grams of MgO over 1 mole of MgO. I was thinking that there was a farmer had a dog. You know what is VIGO? I don't know. MgO. MgO. I know. Oh, the things. How many sig figs? 2. Follow. And that's a good thing. But does the 0.50 grams kind of, it feels right. Okay, the conservation of mass. And then sometimes students will say, Mrs. Snipes, if I can deduce it from work I've already done on a test or something like that, is that okay just to go for the, and yeah, that'd be okay, but I'll never give that to you on a test. So it's a good check though. Yeah, the conservation of fill in the blank. Conservation of matter, conservation of energy are the biggies. So conservation of matter, we have our 2 reactants. That was your magnesium, and the 0.20 grams was your O2. Okay, so it better be 0.50 grams. Yay! So it's kind of a check. It actually, we're going to do a few more problems where a check is what it sounds like. It's a check. So let's do this one. And just to remind you how this works, we could verify that the number, bless you, the number of phosphoruses and chlorine on both sides are the same. I got what, 4 phosphoruses and 12 chlorines? I got 4 phosphoruses and 12 chlorines. But before we do this problem, I want you to kind of remember, just kind of be thinking what those ratios are going to look like. So for instance, I have, if we pick on Cl2 and PCl3, I have 6 moles of Cl2 would need to react for every 4 moles of PCl3 formed. Okay, if I want to pick on P4 and PCl3, I could say that 1 mole of P4 will react for every 4 moles of PCl3 that are formed. And kind of the way the pattern goes in working these grams to grams problems, that ratio is going to be kind of in the heart of your problem. All right, so let's work a problem. We already saw those videos just the other day. Let's work a problem. It says what mass of P4 is needed to react. So I'm going to find my P4. I'll put question mark grams. What mass of P4 is needed to react with 1.25 grams of Cl2. So the next slide, I'm going to knock out the molar masses of everything, but I can go from grams of Cl2 to moles of Cl2 using its molar mass. And then I can go from moles of Cl2 to moles of P4 using the stoichiometric ratio. And then I can go from moles of P4 to grams of P4 using its molar mass. So do you guys have this slide already? You do have these molar masses?
No.
Okay, great. Okay. So the molar mass of P4 is 4 times 30.97, 123.88 grams per mole for P4. For Cl2, it's 2 times 35.45 or 70.90 grams per mole. And for the product, PCl3, it's 30.97 plus 3 times 35.45 for 137.32 grams per mole. Notice that the molar masses, and this would make sense, the molar masses are independent of the equation or the reaction. I mean, the molar mass for PCl3 is always going to be 137.32 grams per mole, whether it's the product in this reaction, whether it's a reactant in some other unrelated reaction, that's the molar mass. Sometimes what I run into, and I don't want to throw you off, it's like, this is what sometimes students do, so I'm like, oh, you do that, so don't do that. But sometimes students for the molar masses want to somehow incorporate the stoichiometry for the specific to this reaction, the stoichiometry. They want to put the stoichiometry in the molar masses, but it's not. It's independent. All right, so here we go. We said we're going to start with the mass of Cl2, and then what's the next term? Yep. The molar mass of Cl2, perfect. 1 mole of Cl2 over 70.90 grams of Cl2. Awesome. So now we want to go, this is the heart of our calculation. We're going to use the relative amounts of Cl2 and P4. So what does the rate, that stoichiometric ratio look like?
1 mole over 6 mole.
Yep, 1 mole P4 over 6 moles of Cl2. Don't forget to label your stuff. Yes, very good. So now we have moles of P4, but we want grams of P4. So now what do we use? Yep, the molar mass of P4, exactly. The molar mass of P4 is pretty heavy, 123.88 grams of P4 for 1 mole of P4. So you're good about showing all your work, especially for homework and for the tests and stuff. And I will be looking for these. It's not sufficient just to say, for instance, we pick on the stoichiometric ratio. You can't just say 1 P4 to 6 Cl2. It has to be 1 mole of P4 and 6 moles of Cl2. All right. How many sig figs? You guys agree? All at 3. So 0.364 grams of P4. So we're going to do a follow-up question. Let's see, 1.25 grams of Cl2. We just now did this problem. You'll have to react 0.364 grams of P4. So the follow-up question is going to be, what's the mass of product form? We could add them together, but we're not going to do that. Okay, so here's the follow-up question, and it says, what mass of product, what mass of PCl3, so question mark grams, of PCl3 can be formed with reaction of, again, that 1.25 grams of Cl2, and this says sufficient P4. So we know that sufficient means enough. Enough, P4. That's what sufficient means. So you know it has to be greater than or equal to, what was that, 0.385? What was 3 what?
6.4.
6.4? Okay, thanks. That's kind of what sufficient means. But like I said, we can add these together and go ahead and get that, but we're not going to do that. So instead, we're going to go from grams of Cl2 to moles of Cl2. And we're going to go from moles of Cl2 to moles of PCl3, and then we're going to go from moles of PCl3 to grams of PCl3. Totally. So here we go. Our starting term is 1.25 grams of Cl2. What's the next term?
1 mole over 70.9.
Very good. 1 mole Cl2 over 70.90 grams of Cl2. Great. And we're on our way to, now here's where we're gonna, this part right here, we're gonna focus on the stoichiometric coefficients. So what's that next ratio look like?
4 moles.
4 moles of PCl3 over 6 moles of Cl2. And again, I get the whole kind of reduction thing, it's the same thing as 2 over 3, but it means so much more if you go 4 over 6. Good deal. So then what's the last term to finish it up? It's all downhill from here.
37.32 grams.
Very good. 137.32 grams of PCl3 for 1 mole of PCl3. Never say pigs. Yep, 1.61 grams of PCl3. So this is a very busy figure from your from OpenStax. It's kind of cool though. So let's look at this. We have used, if you want to go back and forth between mass and volume, you use density. This is something that we actually talked about in Unit 1. If you want to, let's see, where's another example? This one down here. If you want to go back and forth between number of particles and moles, we use Avogadro's number. If you want to go between moles and mass, you use the molar mass. If you want to go between moles and moles, use the stoichiometric ratio or stoichiometric factor. Molar mass and mass, moles and mass, molar mass. And I think we've probably talked about this one too. The ones we haven't, we've talked about this one. The ones that we haven't talked about yet are deal with solutions, and that's these molarity ones. So I guess everything else we've kind of talked about. So wait for those. So it's kind of a fun little thing. Speaking of fun little things, so here's where you guys can earn 10 extra credit points, and you guys got time, so nobody leave until this is done. You guys are going to work this, and you can work together if you want, or work by yourself. I'm fine either way. But I want you to drag yourself through these multiple series of problems. So let's see what we got. The thing is, we have what? Two reactants and 3 products, right? 2 reactants and 3 products. So you have all sorts of possibilities of different sorts of going from the mass of something to the mass of something else. So for this first one, it says, assuming, by the way, all the starting places is 0.143 grams of O2. So if you have that mass of O2, what the first one is, I'll call it 1A and 1B, is 1A will be this one. What is the mass of TiO2, question mark G, this was. And then 1B is this one. What is the mass of that reactant? And then, for 10 extra credit points, remember, all this is, then we go to, it says, based upon, again, the 0.143 grams of O2, what mass of the other products would be produced? So we'll make this 2B, question mark, grams. That's 2B. And this one is question mark grams. Did I do that right? I did that wrong, sorry. Final answer, TiF4, that'll be 2A. And this will be 2B. So again, you can work together, and I'll put some answers up here, but I'd like to see you guys pull yourselves through this before you go, and I'll be walking around if you have any questions. But you guys have all these, right? Okay, good. That makes life easier. There's an app for that. There's literally an app for this. Are you serious? Instead of me standing up here and talking at you.